Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures in computer architecture. We have been looking at the details of the control unit. That is the topic that we have been focusing on. In the previous lectures, we have been looking at pipelining as the major aspect, as one of the important aspects of control unit. So, we have looked at the basic idea of pipelining, we have looked at the an example of a pipelined architecture, the MIPS pipelined architecture. We have looked at some of the challenges that come in a pipelined architecture, hazards, and we also looked at some solutions. So, what we will be looking at in today's lecture is a little bit more on instruction level parallelism. We already know that pipelining itself is a form of instruction level parallelism, but what we will look at today is something more than pipelining. So, what are the different ideas that have been developed with respect to instruction level parallelism, and what actually goes into today's processors in terms of instruction level parallelism. So, when we talk of instruction level parallelism, what we essentially mean is that more than one instruction is being executed simultaneously. So, that is what we are looking at. So, coming to details of instruction level parallelism per se. So, as we said, one of the first techniques of instruction level parallelism is pipelining itself. So, where again we are executing multiple instructions in parallel, only thing is that the different instructions are in different stages of execution. So, what are the techniques that we can use in order to increase the instruction level parallelism? So, that is what we need to first understand. So, one way of doing that would be to just go for a deeper pipeline. So, what do you mean by a deeper pipeline? That is, you can increase the number of stages that you have in the pipeline. So, we know that if we increase the number of stages, that is for a given amount of work to be done, if I increase the number of stages, then lesser and lesser amount of work will be done per stage. So, when lesser and lesser amount of work is done per stage, so what we can end up doing is we can shorten the clock cycle. So, because you are having less amount of work to be done, you can do the same thing within a small amount of time, which means I can use a shorter clock cycle. So, if I use a shorter clock cycle, I can use a higher clock frequency, and because I use a higher clock frequency, I can get better performance. So, this is one way in which you can improve performance by increasing the ILP. So, instead of using 5 stages, if I use 10 stages, it would mean that I would be able to execute more number of instructions in parallel. So, that is one way of improving performance. Another way of improving performance is what is referred to as multiple issue. So, what we are talking about here is that we will replicate the pipeline stages. That is, instead of having a single pipeline, we will have multiple pipelines. So, instead of just having one pipeline, we will have multiple pipelines, and each of these pipelines will be executing different instructions, and they can all work together. That is, you will start multiple instructions per clock cycle. So, you can look at it as having multiple pipelines, and to each pipeline you have a set of instructions that are being supplied. So, what will happen is we will be able to start multiple instructions per clock cycle. So, obviously, it means that multiple instructions will be able to complete per clock cycle. Therefore, more than one instruction is again executed per clock cycle. Of course, this requires additional hardware in the sense that we are going to have multiple pipelines. But given that we have enough number of transistors available on any given chip, and therefore, we can have more hardware that can be added onto the chip, it makes sense to add additional pipelines, multiple pipelines, and go for a multiple issue architecture. So, this is what has happened in terms of instruction level parallelism over the last 15 to 20 years. Okay. So, what is happening here is that the moment we say that I am issuing multiple instructions per clock cycle, the CPI factor that we talk about, that is the number of clocks per instruction, becomes less than 1, because on an average I am executing more than one instruction per clock cycle. So, therefore, number of clock cycles per instructions will be less than 1. So, what we therefore now talk about is not clocks per instruction, but we talk about instructions per cycle. Okay, instead of saying number of clock cycles per instruction, we now look at the inverse of that, which is the number of instructions that are executed per clock cycle. So, if we talk about, for example, a 4 gigahertz clock based processor which has a 4-way multiple issue capability. What do I mean by this? this means that it is a multiple issue. So, which means I can issue or I can start multiple instructions in a given clock cycle, and when we say it is a 4-way multiple issue, it means that I can start 4 instructions in one clock cycle. So, with this you will be able to achieve a peak, a CPI, that is a clock per instruction of 0.25, assuming that in an ideal pipeline you will have one instruction being completed out of every single pipeline. Since there are 4 pipelines, there will be 4 instructions coming out every clock cycle. So, the instructions per clock cycle, your IPC becomes 4. Your CPI will be 1 by 4, which is 0.25, or you can look at it the other way around. The CPI is 0.25 and the IPC will become 4, right. And given that you are executing at 4 gigahertz, you will be able to execute about 16 billion instructions per second. So, that is the kind of performance that we can get with this kind of an architecture. Okay. Of course, what we are talking about here is an ideal case, but in practice there will be dependencies. We have already seen different types of dependencies, right, data dependencies and control dependencies, and because of these data dependencies and control dependencies, you may not get exactly the peak IPC of 4, but you may get something which is less than that. Nevertheless, you will get something much more than a simple single issue pipeline architecture. Okay. Now, coming to multiple issue, and we will look at what are the different ways in which a multiple issue architecture system can be designed. So, when we talk of multiple issue, there are 2 essential schemes that we look at. One is called as a static multiple issue mechanism, and the other is a dynamic multiple issue mechanism. Okay. So, when we talk of a static multiple issue, it means that the compiler will group the instructions that can be issued together. So, that is when the compiler compiles the program and generates the instructions that can go into the architecture, into the processor, it will group the instructions which can go together into the pipeline in parallel. So, we call these as issue slots. The term that is normally used is issue slots. So, we package the instructions which can be issued together into issue slots, and it is the job of the compiler to detect and avoid hazards. So, the compiler will have to make sure that it is able to schedule the instructions correctly and say that if these 2 instructions are executed together, of these 4 instructions are executed together, it will not result in any hazard and the execution will take place correctly. Okay. So, this is a static multiple issue architecture. Another option that we have is a dynamic multiple issue architecture, wherein the CPU itself will examine the instruction stream and will choose which are the instructions which can be issued in each clock cycle. So, this means that the CPU will actually pick up multiple instructions from the instruction stream, and out of those instructions it will choose which instructions can go in parallel. So, the compiler here can help, that is, if the compiler itself reorders the instructions and gives it to the processor, it becomes easier for the hardware, for the CPU to pick up these instructions. Okay. So, the compiler here can help by reordering the instructions, but it is still the job of the CPU to resolve the hazards which can occur at runtime. So, it will use some advanced techniques to resolve the hazards and make sure that it is able to pick up instructions which can be executed in parallel. Okay. So, there are again some standard advantages that we talk about when we go for a static multiple issue, and standard advantages that we talk about for a dynamic multiple issue. So, as usual in a static multiple issue system, the hardware need not be very complex, it need not worry about reordering it, or it need not worry about using any special techniques for resolving hazards. So, the hardware can be kept simple if we go for a static multiple issue, but often the compiler can only do so much, in the sense that the compiler may not be able to resolve certain issues, certain dependencies which will actually be known only at runtime. So, in those cases the compiler may not be able to really identify the dependencies correctly, okay, in which case it will not be able to drastically go and make any changes. So, it will be a more conservative approach that will have to be taken by the compiler. So, static multiple issue has certain advantages and disadvantages, and dynamic multiple issue also has certain advantages and disadvantages. Okay. So, let us look at a little bit more in detail about these 2 techniques. So, when we do static multiple issue, as I said, the compiler will group the instructions into issue packets, and all these instructions will be issued in a single clock cycle. Okay. So, that is what will happen, and the number of instructions, how many instructions actually go in a group, that will be determined by the pipeline resources. So, one way of looking at the whole thing, one of the standard architectures that we have under this category of static multiple issue is what is called as a very long instruction word architecture. So, what is very long instruction word? You can look at this issue packet, you can think of an issue packet as a very long instruction which consists of multiple concurrent operations. Okay, so instead of having just one instruction, we are saying I specify two instructions together and say that these two together is actually one instruction word, which consists of multiple concurrent instructions that can go together, that have to be executed together. Okay, so VLIW is one standard architecture technique which uses the static multiple issue mechanism. Now, what is it that the compiler has to do in order to help the static multiple issue? So, the compiler will have to remove all the hazards, at least some of the hazards. That is, it will reorder the instructions into issue packets and make sure that within a packet there are no dependencies. So, remember that now all the instructions within a packet, within an issue packet, are all being executed simultaneously. So, if they are executed simultaneously and if you had dependencies between these instructions, obviously they cannot be executed correctly. So, the compiler has to make sure that the instructions which go within a packet have no dependencies between them. But there may be some dependencies between packets. Okay? But if there is a dependency between packet, then which can, of course, the dependency can vary when the ISAs vary, but the compiler must know that, and it should sufficiently provide the distance between the instructions so that the dependency does not result in a hazard. Okay. And what the compiler would normally do is, it could also do padding with no ops. Remember that no ops stand for no operations. There is instructions which actually do no operation, but you might just add these no ops in between if you just wanted to make sure that for taking care of these dependencies, so nothing will be done in a particular instruction, but there will have to be, you can't leave a particular slot as empty. So, within the issue slot you may just provide some no op instructions in order to fill the issue slots. So, you can see that this actually results in some kind of an inefficiency, because you are unnecessarily putting no ops and no operations getting done in that place. But the advantage I get is that, let us say I have 4 slots in my issue packet. Out of the 4 slots I may be able to fill 3 slots and I may leave only 1 slot free. So, in which case I am still able to get 3 instructions being executed in parallel. So, you do get the advantage, but you may lose some slots because the compiler will have to find these independent instructions that can go in one issue packet. Okay. So, let us just take one example of our MIPS pipeline itself with a static schedule for a dual issue processor. So, let us assume that we have 2 issue packets and you have one ALU or branch instruction and one load store instruction. Okay. So, we will assume that it is 64-bit align and the ALU or branch then load store, and you will pad an unused instruction with a no op. Okay. That is, we are assuming that out of this 64 bits, first you will have the ALU branch instruction, then the load store instruction. That is, in a packet now we are packing 2 instructions. So, the first instruction we are saying will be an ALU or a branch instruction, and the second instruction in that packet will be a load store instruction. So, let us look at how the pipeline stages will progress from this figure. At address n, I have an ALU branch and I have a load restore instruction. So, when I am picking up, I will be basically picking up these 2 instructions together. So, the 2 instructions will enter the instruction fetch stage together. The 2 instructions together will go to the decode stage, together to the EX stage, together to the mem stage, and together to the write back stage. Next 2 instructions will be picked up in the next clock cycle. So, you can see that these 2 will be in the IF stage. So, you can just compare this with our simple pipeline where I would have had only one instruction in each stage. Now, you can see that there are 2 instructions in each stage. So, 2 instructions in the IF stage here, 2 instructions in the ID stage, and so on. So, you can see that every clock cycle, if you look at how many instructions are being completed, 2 instructions will be completed. Okay. So, this is how it will appear if you are looking at making our MIPS as a dual issue pipeline. Let us look at our the MIPS pipeline modified for this dual issue. So, as you can see, what is it that we had to change now? In the instruction fetch stage, we need to pick up 2 instructions at a time. Okay. So, you can see that from the instruction memory, instead of having one instruction coming out, we are showing 2 instructions coming out. So, there is one additional instruction that is being brought out, and both these instructions will be stored in the latches, and you can see that both the instructions will be decoded. So, in the decode stage, which is over here, you can see that in addition to the black lines which correspond to a single instruction, there is another blue line that is shown here, which shows that the 2 instructions will be decoded, and both the instructions, whatever registers have to be read for that will be done. So, you can see that the registers can be one set of registers, or you may have an extended set of registers, but the other logic that we have is kind of duplicated. So instead of one sign extend logic, you can see that there are two sign extend logic that are provided, one for each of the set of operands that you have. The first instruction will have one set of operands, second will have another set of operands. So we have to provide both these things. Similarly, if you look at the EXE stage, instead of having one ALU, we now have two ALU registers that are, two ALU units that are provided. So that two operations can take place in parallel. Since we said that the way we are grouping the instructions, there is one load store and another ALU or other operation. Now since we have a load store and an ALU operation grouped together, the ALU operation will have no job to be done in the memory access stage. So the load store can access this data memory without any problem. And then again in the write back stage, you will see that the write back gets done correctly. So in the write back stage, again you can see there will be two lines coming out, the data to be written from both the instructions. Both the instructions results are carried back to the register file and they will be written. So this is what we see as the architecture for our MIPS processor with a static dual issue. So you can see that I said there are two pipelines, right? So this is what we mean by the two pipelines. There are two instructions issued, two instructions decoded, two instructions executed, and you have all the logic required for doing that. So we will take a small break now and then come back and continue. Welcome back after the break. So we were just looking at a dual issue MIPS architecture. So now let's look at hazards which can occur in this dual issue MIPS architecture. So now we see that there are more instructions which are executing in parallel. Okay. So you could have a data hazard in the EX stage. Now we saw that forwarding avoided the stalls with when we had a single issue processor. But now you can't use the ALU result in the load store in the same packet. Suppose we had these two instructions, add T0, S0, S1 and load S2, 0 of T0. Now look at this, these two instructions, this is one add and a load instruction. Now we have said that an add and a load can actually go together in a single clock cycle, but these two, that this add and this load cannot go together in a single clock cycle. Now why is that? That's because there is a dependency between this add here and this load here. You can't use forwarding here because these two are being executed simultaneously. So the value produced by this T0 is required in the same stage by the load for the address calculation. Therefore, these two instructions cannot go together. So essentially what you will have to do is when you have these kind of instructions coming together one after the other, you will have to split it into two packets. So effectively it is like having a stall. Okay, so that is what you will have. So you may have some inefficiencies that are introduced because of hazards which could occur if you did not take care of these correctly. Okay, so when you have two instructions both in the EX stage which require the same data in the EX stage, you will have to split it into two packets. Okay. Similarly, if you look at the load use hazard, okay, there will still be one clock cycle use latency, but now you have two instructions. Okay, that is another thing to remember. So essentially what we will need is you will require more aggressive scheduling will be required, that is ordering of these instructions and other things which are normally done by the compiler will have to be done much more effectively. So that is what we will see, that is what we understand when we look at these kind of dual issue or multiple issue architectures. So again this gives you another, whatever we talked about just now, a sample set of instructions where we are showing that we will have to necessarily issue only one instruction per clock cycle because of the dependencies. So let's look at what we have here. So I have a load and then there is an add u which is adding a scalar element in $2, and then you have a store which is storing the result which is produced by this add u, and then I have an add I which is independent of these. I have $S1, -4, basically it is decrementing a pointer, and then we have a branch, a conditional branch which will loop back to this. Okay. So now let's look at how this can be scheduled. Now the load will have to take place. Okay. Now remember, load stores are placed in the second slot and the first slot will have the ALU or the branch instruction. Okay. So these are the two instructions which are going together in each cycle. So in the first cycle I have placed my load instruction here. There is no instruction that can go here because this add cannot be executed in the same cycle as the load because of this dependency. So your load alone can go in this clock cycle and this slot is empty. So it is what you are substituting there is a no op instruction. So no op instruction indicating that no operation will take place here and only this load will get executed in this first bundle. The second bundle, you can see that there is a rescheduling that is happening here. Now because the load is producing the T0 and to use the output of the load we need one clock cycle delay, I can't schedule it in clock cycle number 2 itself. So instead what you do is you are scheduling it in clock cycle number 3, and this instruction add I, which is independent of the others, you can reorder that and bring that into the second clock cycle slot. Okay. So I am bringing it over here in add I $1, $1, minus 4. So this decrement pointer, because this is independent of any of the other values, you change this over here, you bring it here, and in the third clock cycle I can have my add U, which is going to use the value produced by the load. So load is loading into this register, that value is used in this clock cycle, in the third clock cycle by the add U. Now again see that there are no other load store instructions which are going here, so again we have no ops in these two clock cycles, and then there is a branch instruction which is coming in the fourth clock cycle along with the store. Okay. Now remember again, this store is storing the value which is produced by this add. Now add was completed in clock cycle number 3 and then we are storing it in the fourth clock cycle, you have the store here. Okay. So these two things are coming in clock cycle number 3 and clock cycle number 4, because again there is a dependence. But what you also need to note is, if you look at what is happening here, we said store word in the address 0, 0 of S1, and following that you are actually decrementing S1 by 4. Okay, you had add I S1, S1, minus 4, which means you are decrementing S1 by 4. But what we have done is we have moved this add I earlier, right? We have shifted this add I from this slot to this slot. So which means the value S1 which is used by this SW, the store instruction, is now becoming different. So we have to adjust for that. So which is why you will see that the store word here, instead of storing into 0 plus S1, is now storing into 4 plus S1. Now why 4 plus S1? Because we have already done this minus 4 earlier. So to get back to the same address, I need to add 4 here, so that I will store in the correct location. So these kind of correct address calculations and pointer adjustments or the index adjustments will have to be done by the compiler in order to do the rescheduling. So this is what you will see as some additional work to be done by the compiler. So in this case, if you look at the total instructions per clock cycle, there are 5 instructions which are getting executed in about 4 clock cycle. So we are getting an effective IPC of 1.25, whereas the peak IPC could have been 2, because it's a dual issue processor. I could have got a value of 2, but because of dependencies here, you are getting an IPC of 1.25. If you had more number of instructions to fill this, then obviously you can increase your IPC. Okay. So the compiler normally uses certain techniques in order to find more instructions it can put into those slots, so that we do not have these no-op slots which are provided. So one technique that the compiler uses is called as loop unrolling. So what we do here is, we replicate the loop body in order to expose more parallelism. So that is, if you look at this is a very tight loop. We are only doing one operation per iteration. Okay. So what we will do instead is, instead of calculating only one value here, calculate 2 values. So in that case, what will happen is that the total number of times the loop gets executed will be reduced, but you will be looking at 2 different iterations essentially being done within a single loop. So this is referred to as loop unrolling. Say for instance, we have x of I is equal to y of I plus z of I. I have a for loop where I say for I equals 1 to 100, x of I equal to y of I plus z of I. So I am going to change this to for x equals I equal to 1 to 100, but what I will do now is, within the body of the loop I will do x of I equal to y of I plus z of I, and I will also do x of I plus 1 equal to y of I plus 1 plus z of I plus 1. Only thing is, now my I value that I had, instead of incrementing it by 1, I will increment it by 2 for every loop. So 50 times a loop will get executed, but in every loop, right, 2 iterations, right, I and I plus 1, both these values will get calculated. So now when I translate this into the instructions, for I and I plus 1, since I am doing 2 operations, for I will have to do a load operation, for I plus 1 I will have to do a load operation, for I will have to do a addition, for I plus 1 I will have to do an addition. So the number of instructions you have within that loop will increase. So when I have more number of instructions in the loop, now the compiler can reorder the instructions and make sure that it is able to fill all these additional slots that I have when we are using this multiple issue based architecture. Okay. Another advantage that we also get is that the loop control overhead is reduced. So what do we mean by this loop control overhead? So if you look at this loop that we just saw, you can see that for every 5 instructions there is a branch that is coming in, right. So and for doing the branching we have to do one subtract and then do a branch. So, out of 5 instructions, 2 instructions are for the branching and 3 instructions are the only ones which are actually doing the work that we need, that is loading some value, adding something and storing the result. The other 2 instructions are essentially overhead because we want to execute this as a loop. Now, instead of doing one operation in one loop, if I were to do 2 operations within the same loop, now you look at what my overhead will be. This overhead will still remain 2, but totally I would have done 6 instructions would have got executed and there will only be 2 instructions overhead for that. So, instead of 3 instructions and 2 instruction overhead, I will have 6 instructions, useful instructions, and 2 instruction overhead. So, you can see that the total number of overhead instructions that I have, the loop control overhead instructions I have will be reduced, okay, overall, in the overall fashion it will be reduced. So, that is one of the advantages when you also go in for this loop unrolling. So, this is a standard technique that is used by compilers in order to get your instruction level parallelism whenever it is doing static scheduling. And when you do this, it will obviously use different registers per replication, okay, we call it as register renaming. You rename the registers and you can avoid the loop carried anti-dependencies, okay. These are all things which are done when we do loop unrolling. Okay, so this is just an example again with this loop unrolling technique that we have. So, you can see here the same loop we are looking at, but now what we have done is we have unrolled the loop 4 times, okay, that is 4 operations are going to be performed within this one single loop, okay. So, look at what we have here. You have first one add I, you can see how many loads are here. We are loading 4 different values. So, loading into different register locations T0, T1, T2 and T3, okay. So, this is for loading from 0, this is loading from 12, this is loading from 8, this is loading from 4. So, 4 different loads have come in and the corresponding adds. So, once you have done a load, 2 cycles after that we can do an add. So, you can see that when I am doing this add, instead of leaving the slot empty, I am loading another instruction here, okay. So, this load again will be used in the next slot here, this load will be used in the next slot over here. So, you can see this here. So, T0, T1, T2, T3, the values that are loaded are used in clock cycle number 3, 4, 5 and 6. And when I do this, okay, once this add has been done, this corresponding store can be done in another clock cycle, 2 clock cycles away. So, see what is happening here, there is a store being done here, store being done here, store being done here and a store being done here, and along with this store the branch calculation can be done and the loop adjustment, the pointer increment that we did, right. So, that is put in this clock cycle and accordingly we will make the necessary changes for the addresses, okay, the addresses are changed appropriately, okay. So, once you change the addresses appropriately and adjust for the changing of the pointer, so you can see that number of no-ops that we have is reduced and total number of instructions being executed per clock cycle will increase. So, look at what is happening here, altogether 14 instructions are executed in a total of 8 clock cycles, which means I get an IPC of 1.75, okay, which is closer to 2, but of course, this is at a cost of registers and codes, that is we are using more number of registers and the size of the code will also increase, okay. This is what happens in the loop unrolling mechanism. To summarize, what we have looked at today is one technique of doing instruction level parallelism beyond pipelining, okay. So, we have looked at something which is beyond pipelining. Of course, we are still using pipelining, only thing is not a single pipeline anymore, but we are using 2 pipelines together or 2 or more pipelines together. So, we saw an example of how multiple instructions can be scheduled per clock cycle. So, we said there are 2 approaches, static approach and a dynamic approach. So, what we have looked at is the static approach, which is a compiler supported approach. So, in this compiler supported approach, we saw how the compiler can use a technique called loop unrolling and try to schedule more number of instructions in a given clock cycle. Set of questions to look at what we have covered today. Question number 1, what is meant by ILP? Question number 2, when considering multiple issue, why do we consider IPC rather than CPI? Question number 3, what is a VLIW processor? Question number 4, how can compiler help for finding instruction level parallelism? Thank you.